the term is created with what we've done before. So if you look at the notes for Lagrange that you've taken, how was this similar to what we've already done with polynomials? The factorial, yep. So you had the exponent match the factorial on the bottom. Okay, what else was similar? Okay, so you had like the center. You'd have like, oh, this is centered at something, and so that was the same if it was centered at 2. Then you'd have x minus 2 to the 5th or 5 factorial. Okay, what else was similar? Is there any derivative that goes into part of making the term? So this says it's the 5th derivative, right? The 5th derivative. We know it's the next term, right? If you're doing the approximation with like the first 4 terms, then the error would come from the 5th term. So that's like just like what we did yesterday. So when you create that 5th term, you have the 5th derivative times x minus 2 to the 5th over 5 factorial. So that is just what we did. We have done that. That's not new. But what's weird about it? What have we not done? Yeah, we've never had the derivative on an interval before. We always had the derivative just evaluated specifically at the center. It was always the center's 2, you plug in 2. You never had to wonder what you were plugging into your derivative. Does that make sense? So creating the term is almost exactly the same as what we've done this whole time. Almost. The funky part is that whatever interval is given in the problem, you're looking at the max value of the derivative on that interval. That's the weird part. That's the part that students hate, is that it's not as straightforward. You don't just walk into the problem, go, the center's 2, I plug in 2. You have to look at the problem and say, what's the interval? And then you have to know the function well enough to say on that interval what value is highest. Does that make sense? So you don't just say center 2, plug in 2. You say, okay, I've got a function. Now here, do you even know what the function looks like? No. So for something like this, they make it easier on you by just telling you. Plug in 0.3. So sometimes they'll do that. And then sometimes they'll do something like they'll use a sign graph where we know that 1 is the highest possible number it could be, so we're just going to use a 1. Even though on the particular interval we were using 1 was not the highest value. We're just going to use a 1 because that's the highest possible value we could ever have with a sign graph. And it's lazy math, but it's the common practice. Everybody does it. Okay, so let's try the next problem. We're just going to remember with Lagrange that we know how to build the term. We know it's the derivative. We know it's x minus the center to the same exponent divided by the factorial. The only difference now is that instead of being able to take the derivative and evaluate it straight at the center, we now have to look at the derivative on an interval, and we have to take the max value on that interval. The highest y coordinate on that interval. Does that make sense? That's the only difference. It's weird, and we just memorize that little part of it. Okay? Does that make sense? So that's the weird part about this. That's what makes people uncomfortable. And if you need to remind me to go back and explain that again, say, Ms. Rice, what do people get uncomfortable about today? And I'll go back and I'll talk through it again. Okay? Because making the term, we've done that before. We've done that, and you guys know how to make the term. So derivative, x minus center to the 5th over, we've done that. That's comfortable. The weird part is the interval. And we can do that. We can learn how to do that. Okay, so let's turn to example 3. It says, write a 4th degree Maclaurin polynomial for e to the x. That's going to be easy for us because it's all written on the board because I never erased it. So e to the x is what? Yeah, x cubed over 3 factorial. And then 4th degree, so x to the 4th over 4 factorial. Okay. Use your polynomial to approximate square root of e, which if we were to rewrite that, because this doesn't say e with like radicals over it, it's e to an exponent, so we want to know what we're plugging into the exponent. So if I wanted to rewrite square root of e as e to an exponent, what would it be? E to the 1/2. So this is actually e to the 1/2. Okay, e to the 1/2, which means we are taking our function and what are we plugging in? 1/2. Let's say the function with 1/2 plugged into it. So I don't want to type 1/2 that many times, so I'm going to do 1/2 and I'm going to store it as x, my calculator, and then I'm just going to type in the x's. I'm going to type that as fractions though, so x plus. Okay. Everybody got it typed in? Yes? Yes, yes? Okay. So I got 1.648. Is that what we got? 1.648. Okay. All right, now it says find the Lagrange error bound for the maximum error when the absolute value of x is less than 0.5. So we need to think about how to write this as an interval. So it's probably been a while since you've thought about how to take absolute value inequalities and write them as an interval. So I'm just going to remind you. This is how I remember it in my head, is I say less than, and so I think less than or greater. So less than is between one number and another. I think of it as making a sandwich. So that means that x is between negative 0.5 and positive 0.5. If it was greater than 0.5, then it would be less than negative 0.5 or greater than positive 0.5. So what you have is you have a number line where you have, here's 0 right in the middle, you've got negative 0.5, positive 0.5, and the arrows are like going towards each other, and these are where your solutions are. If it was a greater than sign, then your arrows would be going opposite directions. So I think of it as less than greater, if that makes sense. That's how I remember it. And so less than, it's between one and the other. No? That's okay. That's how I think of it. So it makes a sandwich. See? A sandwich. Less than? No? Okay. It would be negative 0.5. It'd be x is less than or equal to negative 0.5, or x is greater than or equal to 0.5 if it was greater than. So they'd be going like opposite directions. Yeah. Okay. So our interval is between negative 0.5 and positive 0.5. That's what our interval is. That's what this notation means. Does that make sense? And that's because that's how absolute value inequalities work. Okay. So let's go ahead and look at this. Now, if what we have is that, a picture of this actually. So our graph is increasing, and since we're looking at I looked at just, I don't remember why I highlighted just the positive part. It might just be that I drew it on accident. I think I should have highlighted more. Pretend that I drew, hold on, where is negative 1/2? Pretend that I drew this down here. Okay, so if you look at the graph, this is the graph of e to the x, okay? So we're going to go ahead and we're going to start writing the error so that you guys can see everything. So we have f of 1/2, right, because that's the actual function, e to the 1/2. F of 1/2 minus p sub 4 of 1/2. So this is the notation for error. So the actual value minus the approximate value has to be less than or equal to, and then how do we write it? How do we create the next term? And you don't have to think about Lagrange, just think about how did we create the next term when we were creating polynomials? What would we do? So it's going to be x to the 5th over what? 5 factorial. Okay. And then what always is supposed to go in front whenever we have a Maclaurin polynomial? Or a Taylor polynomial? Yeah, it's supposed to be the derivative, right? And if we're on the 5th term, what derivative is it supposed to be? The 5th. So we're going to say it's the 5th derivative, but because we're doing Lagrange error bound, it's not just the 5th derivative. It's the maximum of the 5th derivative on that interval, okay? So we're going to say max of the 5th derivative, f5 of x on negative 1/2, 1/2. Yep, we're including the endpoints. Good question. Yes. And there's a little, sorry, there's a little dot here for multiplication. We're multiplying that as a coefficient over 5 factorial. Yes.
Will there ever be a time that you're not using one of the endpoints for your derivative? Because this graph will probably use 1/2. But would there be a time when you would use I don't know, 0 for the rest of them?
So as far as like the number that you plug in, you could absolutely end up not using an endpoint. So think about maybe maybe you have a parabola or something, and your endpoints are like parts of the outside, and then maybe the vertex is in the middle or something, and the vertex ends up being the maximum point, right? So you end up using something that's not the midpoint for what you plug in. Does that make sense?
Yeah.
So yeah, so you could absolutely end up not using the endpoints to plug into the derivative. Yeah. Yeah, you cannot shut off your brain when you figure out what the maximum is. Yeah, you absolutely have to use your brain for that part. And this part truly is a problem by problem basis. And what we'll start to realize is depending on the problem, sometimes they'll give us this number, sometimes we'll have a graph to plug it into, sometimes we'll have a table of values to get that number from. This is where they can get creative in the problems to like figure out how to give us the information so we can figure out the maximum of that derivative, because truly they can give us any piece of information to have us figure it out. But remember what I said yesterday? I've seen more alternating series error bounds in FRQs than I have Lagrange. I've seen a couple Lagrange, but I've seen a lot of alternating series. So is this going to be the, like, you are guaranteed FRQ 6 on the BC exam from this unit every year? Like, you are guaranteed going to have an FRQ based on this unit. Is it going to have Lagrange? Maybe like 15% of the time. So it's probably going to have an error bound because it seems to always, but it is often the alternating series error bound. So I'm going to prepare you for this because it happens often enough that I want you guys to not panic if you see it. I want you to feel like you have a good shot of answering it correctly, but alternating series seems to be way more common. So, okay, so we're looking for the max of the fifth derivative evaluated on that interval. Okay, and then x to the fifth over 5 factorial. So let's go ahead and let's start plugging numbers in. So now this problem I find to be ridiculous, and you'll find it to be ridiculous too, because what is the fifth derivative of e to the x? It's e to the x. So we're about to use the function itself to help us approximate the function. It's fine. Do you see the yeah, we're doing circular reasoning. Okay, so let's go ahead and let's do some simplifying here. So we have f of 1/2 minus p sub 4 of 1/2. Yeah. Solve for what? This is just notation. This is the notation for error.
And that's for like any of the times that they're like, find this minus this in absolute value. You're not actually finding.
This is like a synonym. This is a synonym for error. This is like what that means.
Can I search for that, like when they rate, or could you just put error?
You could probably put error. All right, so the max of the fifth derivative on that interval, so now we're looking at, this is the graph of e to the x, but that means it's also the graph of the first derivative, it's also the graph of the second derivative, it's also the graph of the third, and the fourth, and the fifth. And so we know that the fifth derivative looks just like this, and the fifth derivative evaluated, if we look on the interval from negative 1/2 to positive 1/2, we know that the maximum is found at positive 1/2. Everyone agree with that? Maximum is found at positive 1/2. So I'm going to go ahead and say, okay, that the maximum derivative is e to the 1/2. So I'm plugging the approximation I'm trying to find into, yeah, it's silly. Okay, it's silly. But we're going to do it anyway. Okay, times, and then what do I plug in next? Yeah, 1/2 to the 5th over 5 factorial. Okay. All right, and then what do we get for that? We're going to have to use a calculator. E to the 1/2 times That's a decimal. Yeah, a lot of people do this, and then they take this little part and they say equals. Or I would do approximately, actually, because I'm rounding. That's pretty, this is pretty common notation right here. Okay. Yeah.
Even though it says or equal to,
Mm.
but it's like, because it's the same thing, right? Like that's your error, you're just doing it not with numbers.
Mm-hmm.
And I'm like, how can you say equal sign after that?
Yeah. Well, it's like they're saying that this is the inequality, but this little piece is equal to this.
Yeah.
Yeah. Yeah. Okay, so what decimal are we getting? Yeah. There we go. And then we could even check it. We could check our answer too, because so this answer is supposed to 1.648. So if I do e to the 1/2, is supposed to be that far off of, well, that other decimal. What was that other decimal? So if we compare it, that it's just a little bit under, so plus this. And then let's go back and compare. Yeah, it makes it a little bit closer. It's wild, isn't it? Math is wild. Okay. Example 4. Oh, I was comparing the decimals on the screen. You guys couldn't even see them. There. This was me taking our estimate for e to the 1/2 and then adding our error. That's what I was doing. So I was adding the error to see how close it got us. And it took our estimate and it got us a little bit closer to the actual value. So anyway, okay. Example 4. So here we have, oh, it says find an interval. Let's do that real quick. Okay, so we have the square root of e, there's our middle, and we're going to take our estimate and add and subtract the error from it. Oh, I didn't even know that was the next problem. I was already doing it. Okay, 1.648 minus 0.00043, 1.648 plus 0.00043. Now, if you guys were ever doing this on an FRQ for the AP exam, they will not ever let you round a number prior to the end of a problem. So you would want to store the values in your calculator and use the numbers that were not rounded. They will only let you round at the end of the problem. Does everyone know how to store numbers in their calculator? Yeah? Okay. Yeah, they are real big on that. Okay. Next problem. How are your brains feeling now that we've talked about it more? Are you relatively comfortable? Or is anybody panicking? Yeah, yeah. That's calculus, man. Calculus is like, how can I make you feel like you're reading a foreign language but in English? Yeah. All right, the function has a derivative of all orders. Also, okay, so they're giving us all those derivatives. Write the third degree Taylor polynomial and use it to approximate 2.3. Okay, so let's go ahead and get started with this. What should we be writing? This is like taking a trip back to those first couple worksheets we did for the unit, right? So this should be a little bit in our comfort zone. So what do we start with? Mm-hmm. 6. Well, I guess I could put my Taylor polynomial. Okay, so P sub 3 of x equals 6 plus, okay, okay. And then how are we going to use it to approximate 2.3? Volume 2.3. Put the degree. Okay, real nice to be back with a problem where we feel good about it. Okay, 6 plus 4 times x minus 2 minus 2. Anyone else type in the factorials even though you know what the factorial equals? Like, I know 3 factorial is 6, but I still type in 3 factorial. Yes, I know! Look at my calculator screen. There's a 2 factorial there. Tell ya. I just don't trust myself sometimes, you know? Alright, what'd you guys get? 6.921. Okay. Alright. We all got that. We're good with that. Okay. Now they said the fourth derivative of f satisfies the inequality that the fourth derivative is less than or equal to 9 for all x in the closed interval 2 to 2.3. So what are they telling you? Well, they're telling you that your fourth derivative, that the max on that interval from, so if you know what you're evaluating, the derivative for, or if you know what you're evaluating the function for, then you can use the interval from the center to what you're evaluating it for. So if we're evaluating it for 1/2, then we can use, or if we're evaluating it for 2.3, then we can use the center of 2 to the evaluation of 2.3. So 2 to 2.3. And they're telling us that on that interval, the max is 9. So this is them telling us plug in 9. So see this notation? This is fourth derivative notation because they stop using the primes after 3. They do triple prime after triple prime, then they do. This is the fourth. So this is them saying, I'm not going to give you a picture of the function. I'm just going to tell you what the derivative is. I'm just going to flat out tell you. This is my favorite situation because you don't have to guess. You just get to use it. Okay, so let's go ahead and let's build the term. How do we build it? So let's write our error notation first. How do we write our error notation? Yeah, P of 3 is less than or equal to. Oh, I should zoom back out. Okay. Okay, and then what do I write? Let's not plug anything in yet. Let's just write what we're doing so that we have good notes. So we're going to say the max of. So this was, we were on the third term here. So what's going to be the error? The fourth term. So it's going to be the max of what derivative? The fourth derivative. Okay, on what interval? Okay, so we have the derivative times what? So when you create the interval, and this is one thing that I forgot to hammer into you guys, the interval that you can always use, that is safe to use, you can always use this interval, is the center to the number you're plugging in, or the number you're plugging in to the center. That is always a safe interval to use. So on the last problem, the interval we used is fine, but we also could have used 0 to 1/2, because 0 is the center and 1/2 is what we were plugging in. So 0 to 1/2 would have worked perfectly. Does that make sense? And if you look back at sine of 1, the interval they used there, the center was 0 because it was a Maclaurin, and then 1 is what you were plugging in, so they used 0 to 1. The previous problem, the center for that was 2, and they were plugging in 3, so they used 2 to 3. Does that make sense? The center was 2, and you were evaluating the problem for 3. So the interval was 2 to 3. So it's either the center to the number you're plugging in, or it's the number you're plugging in to the center, depending on which number is bigger or smaller, okay? And that might actually be good for us to like write in the notes. Write that maybe at the top or something. We can say the interval let me draw my arrow better right here. Is either the center to the number evaluating, or number evaluating to center. It's always a good interval to use. Does that make sense? Okay. Okay. All right, is everybody comfortable with where we got all this information from? Okay, so now let's go ahead and start plugging in values. Okay, so what's the max of the fourth derivative on the interval from 2 to 2.3? It's 9, because they told us that all of the derivatives on that interval were less than 9. So 9 is the maximum. Does that make sense now what that notation means? So they said all of those derivatives are less than 9, so 9 is the highest, okay? And then what are we going to plug in over here? 2.3 minus 2 to the 4th, okay, over 4 factorial. Okay? And now we can go ahead and plug this into our calculator. Depends on the numbers. So sometimes they make them calculator inactive, but if they did, it would be easier numbers to work with. So 9. Although technically this one's not very bad if we simplified. So we've got 0.003 04. Is that what you guys got? Okay. All right, so if we want to know if f of 2.3 could be something, we just need to create that interval and see if it works. On an FRQ, you could stop right here. Okay. So 6.921. So I went ahead this time to make my decimals more accurate, and I stored my numbers. I don't know if you guys are storing your numbers or if you're using rounded decimals, but we can see if it makes a difference. It depends on, for adding and subtracting, if you put more decimals, you should be fine. It depends if the numbers are being multiplied by something, because if the numbers are being multiplied, then that means that rounding error is being done over that many times. Does that make sense? If you're just adding and subtracting, then that rounding error only happens once. But if it's multiplying, if it's being exponentially, multiplied, then it's an issue. Then it will make a difference, and you not storing will definitely make it so you get the answer wrong. So it's just a good, unless you want to think it through every single time, it's just a good habit to get into to kind of store your answers and always use the exact answer until you get to the end of the problem. Yeah. All right, so could 6.992 be the answer? No, it's not in the interval. So that's a no. Nope. Okay. So at this point, we are ready to move on to practicing the assignment. I'm going to have you guys hold on to the assignment from yesterday until we can go over number 2, okay? Because I do want to talk about that one. I don't want to just ignore it because I know it was kind of a frustrating problem.